In this video, we're going to be talking about Newton's second law of motion, and we're going to be focusing on inclined plane problems. Now, there's a video that I made earlier. I still have the notes, which is a video that I was talking about problems on a straight line. But this time, I want to focus on problems that are inclined, on an inclined plane, right? So the surface is at an angle. So if we have, so let me just draw this, and I'm going to need a lot of space. Let me just draw a triangle, right? And if we have an object that is on this plane, so we're just going to draw our object, and we have this object, and it's, let's say for example that this object happens to be accelerating upwards, right? And I'm saying that it's accelerating upwards to the right so that I can just have all the forces on this particular diagram. Now, there's a couple of things that I want to note before I go further talking about this, is that last time when we spoke, you can check in the previous video, we spoke about friction. And we said friction is a force that happens to resist motion. And if an object is moving to the right, so if I have an object here, so I don't want to mess up my other diagram, I'm just going to draw this here. And I have an object that is moving to the right. Friction will try and resist that motion moving to the left. So friction, you can think of it as a force that always opposes a body that is in motion, right? But when this object is at rest, let's say for example, to move this object, you need 10 newtons of force, right? And this object happens to be at rest. This means that this object is going to resist motion until your force applied is equals to 10 newtons plus. So your force applied has to be greater than 10 newtons. However, the force that is resisting this motion happens to be a force of friction, but not just any force of friction. This is the static force of friction, right? And static basically is for an object that is not moving, right? That is the static force of friction. And when you beat the maximum static friction, so in another textbook, you might see that they say F max, and this just means that the maximum static friction. What that basically means is that if you're applying a force here, and you apply 1 Newton, this object is not going to move because you need to beat 10 Newtons. And then you apply 2 Newtons. This object is still not going to move up until you get to plus 10 newtons. So basically, the maximum force of resistance that we experience on this happens to be the maximum friction, the maximum static friction, right? Keep that in mind. I want you to pay very close attention here. When this object, however, begins to move, when it starts to move, we will now require less force to keep it moving than we did to get it to start moving. So you can actually try it right now. Take an object, put it on the table, and then try to apply a force. Little by little, you will see that it will resist motion. But once it starts moving, it's as if you need far less force to keep it moving than you did to get it to start moving. You know, when you're in a car and you are about to start up a hill, or you're about to start the car and start to move, you start it on gear 1. But when you're on the highway, you use the lowest gear possible, that's gear 6, where it doesn't use as much energy to keep the car going. You can even stop pressing the acceleration and the car will keep going. It requires less force to keep something moving than it did to begin it to move. So that is actually called the force of friction that we need to keep a car, for something that is in motion, is called the kinetic force of friction. So that's F of K, right? And this is kinetic. So we need the kinetic force of friction when the object is moving. And a general note, something that you want to know is that, so let me just get a little bit of space here, move everything to the left, is that the static friction, F of S, is always going to be greater than F of K. It's always going to be a fact. I want you to keep that in mind. So when we have our object here and the object is accelerating to the right with some applied force, it's going to have, because this object is moving, what it has it has kinetic friction, right? I just wanted you to get that. But however, here, let's just say force of friction, just so that I can emphasize on my point here. Now, what other forces are acting on this particular object? Well, we also happen to have the force of gravity that is pulling this particular object downwards. So let me draw this in a different color. There is a force of gravity that is pulling this, that is facing down. So this is force of gravity. And another force that is acting on this object is the normal force. Now, the normal force is a force that is perpendicular to the surface, right? I want you to pay very close attention here. The normal force is a force that is perpendicular to the surface. Force normal is perpendicular to the surface. But we can actually extend this line here to have another line that mimics, we can call this the parallel line, the normal force parallel, right? And it's going to become very useful. I'll show you in a minute. So in this particular case, we have these two. We have this force of gravity, and then we have this normal force. So we can call this Fn parallel, right? These two lines are showing that it's parallel, right? And now I want to zoom in here. I need a lot of space here. So here we have an angle. Here we have an angle that is raising this incline, right? So we have this angle to the horizontal, and we're gonna just call this angle theta. Now this angle theta, I want you to notice here on this line, this surface is represented by this line in this our triangle here. So is represented by this line. So this line is parallel to this line. I know in my drawing it's a bit wonky, I know that, but it's parallel to this line. And because it's parallel to this line, this is 90 degrees. Why is that? Because we have this line parallel to the normal force, and we have this line parallel to the surface, and we know that the normal force is parallel to the surface to the surface. So that means that this is our 90 degrees. This angle theta, right, it actually is here, because this angle here would be 90 degrees. This angle here, so just by looking at it, you can see that if we look further on this triangle, this is the surface, and these are our 90 degrees. And when this I hope that I'm not confusing people here. So if this is our angle theta, right, if this is our angle theta, if we want to find this line, the value of the parallel FG, right? So actually, let me call this, so this is the surface, sorry. So this is FG, but this is the surface, right? Now, something that I want you to note is, if you take an object and you put it on an inclined plane, this object is going to want to come down. There's going to be a force that is going to be pulling this object down towards this direction. The force of gravity that is acting on this particular object is not this force of gravity here. It's the force of gravity that wants to pull it down in this particular direction. Because of that, that's why we have this parallel component of the force of gravity. And the greater this component is, the faster this object is going to be one to pull down. So what we actually care about here, we also care about the FG parallel component, right? Which is the force that is causing this object to want to come down. So what I'm trying to point out is that we have two forces that are pushing this object down. We have the force of friction, and then we have the force of gravity that are both resisting this object to go upwards. So I can say that we have two negative forces. We have Fg minus, and then we have minus F of F. So these are the two forces that are pulling this object downwards, right? Now, if I just look at this part here, if I'm looking at these normal forces that are here, right? If I'm looking at this parallel forces, sorry, not normal forces, parallel forces. If I want to calculate what is the normal force, I use theta. Now, you know that I'm sure you've been taught about this thing called a SOHCAHTOA. SOHCAHTOA, right? And it just helps you with trig ratios to say when you have an angle and our angle is here, right? How do we calculate this component? So we have our 90 degrees. This is the side opposite our 90 degrees. That's our hypotenuse side. So if I want to calculate this side here, I'm going to have to use cos. for this particular side. Now this is adjacent. Whenever I'm dealing with adjacent, I'm going to deal with cos, because if you look here, cos is adjacent over hypotenuse. So we're going to say that if we take this Fg to be 1, I'm going to say that our normal force is equals to cos, so the component of Fn, cos theta, right? And for this particular one here, if we take, this is the opposite, theta, and this is the opposite side, and this is the hypotenuse, and we said we're taking our hypotenuse to be 1, so this would be over 1, but this would just be 1 anyways. I just want to point out that this is 1, and then we focus on this particular this particular part. It's also going to be just, if you look here, it's S is opposite over hypotenuse, so this is going to be sine, right? So this side here is going to be sine. So Fg is actually equals to Fg sine of theta. Now this is Fg parallel, right? Now something else that I want you to note, right, is that the Fg, the normal force, right, is equals to the force of gravity. The reason why this object is staying where it is, right, and it's not sinking into the ground, the reason for that is, if you look at our notes for our previous video, is that the normal force is equals to, you can look up this video, you can look for the video, is the previous video that I posted. The normal force is equals to the force of gravity. And how do we calculate the force of gravity? To calculate Fg, Fg is equals to mass times the gravitational acceleration. The gravitational acceleration in this is 9.8, right? But I just want to point out that it's mass multiplied by the gravitational acceleration. And because that is the case, right, we say that Fg is actually represented by mg, whereas here Fn is also mg, right? For these forces to be able to cancel, for Fg equals to Fn, for this to be equals to 0, Fg minus Fn must be the same thing. So it's now equals to mg minus mg is equals to 0. This will give us 0. If we take mg and then we subtract with mg, we're going to get 0. So it's something that I want you to keep in mind, that Fn is equals to mg. So here is our diagram here. So we have to calculate the parallel gravitational component, it's mg sine theta, and to calculate the parallel normal force component. Because of the fact that the normal force is applied at an angle, we cannot just take mg as the normal force, because the normal force is being applied at an angle, and the object's mass actually has an impact on how much force the surface needs to apply onto the object. I hope I'm making sense, right? And here we spoke about also friction. Then friction, we spoke about static friction, the maximum static friction, and the kinetic friction. So in this particular video, I hope you have a much more deeper understanding of this particular forces here. Now, if I was to add up all of these forces here, how will it look like? So let me make some space. I don't want to erase anything for people. There are people who email me for these notes. If I want to add up all the forces together, I can say that I have the force. So the equation that we use for Newton's second law, we use the equation F net is equals to ma. So the net of the forces, the sum of all the forces, is equals to the mass times the acceleration of this particular object. And I want you to note this, that in the second law of motion, objects need to be moving. If the object is not moving, then we say that F net is equals to mass times 0, because acceleration is 0. So the sum of all the forces must equals to 0. And in other cases, we might have constant velocity. And if we have constant velocity, that means that acceleration is 0, so F net is equals to 0, because there is no acceleration, so F net is equals to 0. In these particular problems, we are usually being asked to calculate some force. So sometimes they could be asking us to calculate maybe the force of friction, the static friction, or whichever one of the case. Now, in my next video, I want to talk a lot more about these types of frictions and how to calculate what friction is. And also, I want to give examples of problems that actually involve this, to talk about how to use the kinetic friction, how to use the static friction, how to use the force of gravity, how to substitute these values into the equation, and all of those type of things. But I don't like keeping my videos too long. This is already 15 minutes. So for now, I'm going to end this video. But like I said at the beginning of the video, if you want these videos to be longer and you want me to group them together, just rather make one 30-minute video that has everything, or one hour long video that has everything. You can just comment down below. But if you're fine with the way everything is, it's perfect. But that's it from my side. Thanks for watching. So in this video, we're going to be talking